there are some additional wordings that come up occasionally that are good to know. Um, I think it's most helpful for these to memorize the picture for the different words, because that tells you what to look for in f of x. And the words are as follows. So when is f of x decreasing most rapidly? And this is a picture, and these are all for f of x itself. That means basically that it's decreasing, and then immediately afterward it's going to start sort of slowing off, tapering off. So what we see here is we see an inflection point from concave down to concave up. F of x is increasing most rapidly in the converse, inflection point from concave up to concave down. F of x is increasing at an increasing rate. Basically it's going up, increasing, but at an increasing rate means getting faster and faster and faster. We can see that sort of concave up shape. Increasing at a decreasing rate is going up, but it's sort of slowing down, it's sort of flattening out. Notice that this is different, decreasing at a decreasing rate. Well, actually, I guess decreasing at a decreasing rate is also flattening out. Although notice that here, decreasing rate is concave down, decreasing rate is concave up. So increasing and decreasing, we sort of know those already. Those are just matched with the increasing and decreasing that we see here. Increasing rate and decreasing rate, though, depend on context for whether or not they're concave up or concave down. Increasing rate gets more extreme, either going up forever or down forever. Decreasing rate sort of flattens out, whether it's increasing, flattening out, or decreasing, flattening out. So let's look at some problems and see where those words come into play. So for this first one, the rate at which people enter a park is given by r of t equals 15 cosine t plus 20 people per minute when t is between 0 and 2 pi minutes. At what time is the rate of entry increasing most rapidly? So as soon as I see this increasing most rapidly, so this is rate of entry, so the rate at which people enter the park is r of t, so it's just what we're given. Increasing most rapidly, inflection point from concave up to concave down. So what this is really asking is, where does r of t have a concave up to concave down IP? So that means we need an r of t line. Let's see, we're going from 0 to 2 pi, concave up, concave down. If we're working with an equation, we have to have a plus minus line, and that would be the second derivative there. Again, 0 to 2 pi. So we need the second derivative, so we're going to start with r of t is 15 cosine, not cotangent. Whoops. Helps if I show you what I'm doing. Plus 20. So r prime of t is going to be 15, let's see, cosine's negative sine. Our double prime of t follows it around to negative 15 cosine t. So the 15 we ignore, we're trying to figure out when that is equal to 0. So divide both sides by 15. And I know that on the unit circle, cosine corresponds to the x-coordinate. So between 0 and 2 pi, that would be at pi over 2, or 3 pi over 2 equals t. If you have a calculator available, you can also pop in your calculator and get the decimal. So pi over 2, 3 pi over 2. I know cosine is positive until pi over 2 because x is positive. Then it's negative, then it's positive again. So concave up, concave down, concave up. And this is one of the only ones where we're looking for a specific inflection point. It's changing a specific way, concave up to concave down, and that happens right here. So the rate of entry increases most rapidly at t equals pi over 2 minutes because r double prime of t changes from positive to negative. So same idea as what we've been doing. It's just that now there's a different word to look at. We can also do similar things involving tables. So the yearly rainfall in a city is given by the table below. So this is year, this is rain in inches. So let's say this is 2000, 2002, 2007, 2013, and here we got 32 inches, 30, 25, and 15. So our question is, does the data support the claim that rainfall, let's call that R of t again, is decreasing at a decreasing rate? Oops, I meant that to be increasing rate, not decreasing. And you can see this being relevant to something like climate change, where we want to see, okay, are things getting worse? We can see that there's less rain over time, but is that rate accelerating or is that falling off? What's the future going to hold is basically what we're looking for. So decreasing, we already know it's R of t. Decreasing at an increasing rate means things are getting worse. It's this shape right here. So we're looking for decreasing and concave down. We have to think for a second about what concave down really means. Decreasing, we know the slope is negative, but concave down means that the slope of secant lines between 2 points keeps getting more and more negative. Basically here it's a little bit negative, then here it's more negative, then here it's more negative, and so on and so forth. So let's just do a little graph, kind of try to guesstimate this, and then we'll do the actual math for it. So here's 2001, 2002, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. 13. Let's see. 5, 10, 15, 20, 25, 30, 35. Okay, so in 2000, right up here at 32. 2002, we're right here at 30. 2007, down at 25. 2013, down at 15. Not looking too promising. This looks like it kind of goes straight and then kind of gets a little shallower, if anything, a little less negative a slope, and then down again. But it's really, we can't quite tell from the graph, so let's go and calculate out the secant lines. So let's do the one from 2000 to 2002. So we've got, and actually I think I put the dot in the wrong place. I think it's right there. So actually this does look a little bit more promising, but we still can't quite tell. So change in y over change in x. 30 minus 32 over 2002 minus 2000. Okay. And then 2002 to 2007. So we've got 2007 minus 2002 and 25 minus 30. So that's negative 5 over negative 5, actually. So really we can just stop right there because this hasn't changed. So the slope of the secant lines don't keep getting more negative. But let's check the others. I think there's only one more. Okay, so that's negative 10. And then 2013 to 2007 is 6. So that's negative 1.6 repeated. So what we see here is we see that basically this was a straight line and then started dipping a little bit. So does the data support the claim that rainfall is decreasing at an increasing rate? That's actually a little bit hard to say, because for these first two, this has not, the rate didn't decrease or didn't increase from this interval to this interval, but it did increase over here. So let's say that. The rainfall decreased at the same rate from 2000 to 2002 that it did from 2002 to 2007. So there isn't support for the claim during those years. However, the slope of the secant line from 2007 to 2013 is more negative than the slope from 2002 to 2007. So the claim is supported for that interval. Notice if there had been something different here, where, for example, this 2002 dot had been down here, so that there was actually a time where it was very clear that the slope of this secant line was less negative than the slope of this secant line, then that would have been evidence saying no, that wasn't the case. Or if this had been like negative 1.3, it would have been very clear evidence. But basically the idea is that you compare the slopes of the secant lines and see if they're getting more negative consistently or more positive consistently if you're working with increasing and increasing rate, or not. Basically, you're looking for consistency across all of them. They should either be getting more negative or more positive consistently.